particular brown dwarfs, white dwarfs, high velocity stars. But tonight she's going to tell us about imaging exoplanets. And so please welcome Gillian Knapp.
Thanks, John. I thank you so much for this invitation and also to visit your wonderful telescope. It reminds me how lucky I've been to have a life in astronomy and how I got into it through an amateur group and learned that being an astronomer was a possibility and somehow managed to fumble my way through the process to get there. I want to talk today about imaging planets. Now, this might seem something that's rather difficult because this is planets around other stars. The stars are far away and the planets will be so faint that you can't see them. This is actually not the case. For many planets within 10, 20, 30, 40 light years, they're plenty bright. First, with the discovery of a planet orbiting a pulsar, the orbit of the motion of the planet changed the arrival time of the pulse ever so slightly on a periodic way that corresponded to the orbit of the planet. The next discovery was rather analogous, actually. It was the small shift in the motion towards and away from you of the parent star itself as it was orbited by a big star. These days, they're able to measure these radial velocities by the Doppler shift to a precision that's better than walking speed. The thought of being able to measure a star moving at a speed like this just blows me away. And is an illustration of how the subject of science advances not just by fundamental ideas, but by big steps in technological capability. And that's what's driven almost all of the great science that's been done in the last 30 years or so. I alluded earlier to being lucky enough to have done this in my life. At my age, I'm lucky enough that every morning when I get up, 10 really amazing things have happened in the field. And that's before breakfast, as Lewis Carroll put it. So the thing I want to turn to today is probably the hardest of all the ways to detect planets, which is actually to take a picture of them. It's hard because you are dazzled by the star, but you actually get to see the planet itself. The other methods that we've mentioned, radial velocity shifts, pulsar shifts, and occultations when the planet dims the star behind it ever so slightly as it passes in front, are all indirect measures. You observe the effect on the parent star itself. Now, there are some interesting theoretical matters at the back of this that I hope you won't mind if I spend a bit of time on. Let's see, is this on? Yeah. This is, I think I pinched it off some page from NASA, sorry for the lack of attribution, as two scenarios for the formation of giant planets, a giant planet being a Jupiter-ish type mass. Beg pardon?
Excuse me, when you, the people on the web can't see the pointer.
Okay.
So could you say top second, speak about what's on the screen?
Do my best.
Thank you. Okay.
The two scenarios shown here, on the left is what's called the accretion model, and on the right is the gas collapse model. As you walk down the frames, what you're seeing is the progress of the formation of the planet. When a star forms, it does so by accretion, but there's a lot of leftover interstellar medium in orbit around it, left in orbit around it. Two things can happen, or at least two ideas for what can happen. One is that the dust grains, which are mixed up with the gas, accrete into planetesimals, little I suppose bricks, fluffy bricks, by sticking together, and gradually accrete more planetesimals and continue in this circular orbit, the reason, as you know, that these sun's planets are in a plane and all going in the same direction, we think it's a formation thing. There's nothing in gravitational physics that says it has to be this way. It was an initial condition. All the planets formed in a disk which was orbiting. So as the planetesimals grow, they then began to accrete envelopes from the gas around them before the gas disappears. The star itself is busy blowing the gas away and emptying the system. And then, instead of the nice systematic circular motions, you may end up with some chaos, because planets pull each other gravitationally too, and they may scatter by close encounters other planets in the system out of into strange orbits. Or we don't see that in our own solar system for the planets, but we do see it in some of the satellites of the planets. And I believe this is the case. I hope none of my colleagues is listening to this on YouTube. That the precision of our computations is still not enough to follow every orbit in the solar system since it formed. So understanding stability on that level is something that's not quite within grasp yet, but we know it's happened because we're here, right? The other scenario has the same disk of gas and dust around the star, but the lumps in it collapse just as they formed in the star in the middle to form big planets. That big planet will then sweep out, empty the disk at its own orbit, because it's catching all the material as it orbits, and make a hollow in the disk. Now, why these two scenarios are of importance is because in this scenario, the way the planets form is different from the way a star forms. In this scenario, the way a planet forms is the same as when a star forms. And stars form by a lump of interstellar medium. Some lump of it becomes gravitationally unstable and collapses. So we would like to know, where do you stop being a star and where do you start being a planet from the formation point of view? So the planets in question that you're particularly interested in are the gas giants, the Jupiter mass and larger planets. Because, as you know, we think that what determines the mass of a star is more or less accidental. It's just whatever lump of interstellar medium. I mean, there's a lot of physics here, but there's a scatter in the size of the lumps, and so you form stars of a wide range of masses. But there is a limit to how massive a star you can form. If this lump that's collapsing is only 80 Jupiter masses of that order or less, it will not become a star, because the pressure on the center is not high enough that nuclear reactions will happen and the star forms. They become just a thing called a brown dwarf. They're a lump of gravitational collapsed matter that's slowly cooling down from the residual heat of formation, but not able to produce nuclear reactions in its center. So is there do planets come down one side of the formation from low masses to high masses and stars down the other? That's what we'd like to know. There's another interesting thing about Jupiter mass planets, and that's to think about their sizes. Jupiter is 1/10 of the diameter of the Sun, roughly speaking, and that Jupiter is the biggest cold thing that can exist. By cold, I mean it's not producing nuclear reactions in its center. Okay, if you have a lump of material, perhaps 80, 100, 150 Jupiter masses, it will form nuclear reactions in its center, and the energy flowing out holds the star up. That energy has expanded the Sun to its present size, and the size of the Sun and its luminosity is determined entirely by the balance between nuclear reactions in the center and gravity coming in. However, if you have no reactions happening in the center, now let's think of coming up from the small side, small bodies. You and I are not stars, however much we might believe it. There is not nuclear reactions going on in our centers. And we have another property too, that if you add mass to us, you also add girth. Am I right? Right. So as we get more massive, our radius grows. However, if we get as massive as about what's the sort of limit? You're pushing Jupiter masses, that growth begins to slow and to level off. Because for every expansion of your waistline that happens with adding more mass, the gravitational pressure begins to crush the matter into a degenerate state. And those two fight each other over the range of about a Jupiter mass to about 80 Jupiter masses, something like that. So Jupiter and things 10, 20, 100 times, 50 times its size, mass, are the biggest cold things you can have. And as you know, what happens when the sun gives up and is not producing nuclear reactions anymore, and suddenly the mass of the sun collapses, it becomes a white dwarf, no bigger in radius than the Earth is. So we're interested in these processes that happen at this degenerate boundary. And who isn't interested in planets? I mean, I defy you to find me a human being on this planet who isn't interested in the idea of planets around other stars. It's a really glamorous and fascinating subject. I want to talk about two projects that I've been lucky enough to be involved in, thanks to my wonderful young colleagues at Princeton. These are efforts to directly detect, make an image of a planet around another star. You're going for the brightest planets. We're nowhere near, I mean not remotely near, getting a planet the mass of the Earth yet. But we can begin to measure Jupiter-type objects. The two subjects two projects, where are we? Come on, Gizmo, what am I doing here?
Push the right button.
I pushed it, I think.
The arrow to the right.
Yep, there's an arrow right there. No. Well, I've got to point at something?
You gotta point at the projector.
Yeah.
Keep talking about
Okay.
the computer over there's hung up.
So the computer likes this picture better than the next one.
Okay.
It was the first project to talk about is something called SEEDS, which stands for Subaru Exoplanets and Disks, something of that sort, detection with Subaru. The telescope which is used for this effort is the 8.2 meter telescope owned by the Japanese astronomical community, their national telescope, sitting on Mauna Kea in Hawaii. Subaru is a very imaginative, a very productive telescope. And one of the instruments that it has put together is this adaptive optics system, AO188, which is the instrument that allows you to begin to pull in to higher contrast than you get just from staring at this great blurry star in the sky. You have to think about what blurs a star and put systems in your optical chain to correct for it. The principal investigator of this project was Japanese professor called Motohide Tamura, who is now also the Japanese PI for the next stage project that I want to talk about in a wee bit. Okay, here's one of SEEDS' results, detections of a planet. Right, there's a lot to parse on this. How does an adaptive optics system work? And what are the things that blur the image anyway? Two things basically: optics, plain old optics. Diffraction, there is a limit to the smallness of an image that you can make with any lens or telescope, which is set by the diameter of the mirror. And why this happens is that the information that gives you that spatial resolution is determined by basically how many information elements you've got across the mirror, how many times the wavelength divides into the diameter of the mirror. So the bigger the mirror, the better. The smaller the diffraction spot. That's a start, that's a good start. But as we all know, that's completely dwarfed by the mess that our atmosphere makes of light as it passes through it. Due to atmospheric turbulence and twinkling, the light is bounced around as it reaches us and spreads out into a great splotch, several arc seconds in diameter, so-called seeing, the twinkling of the stars. How do you get rid of this? Not easily. One of the heart of adaptive optics is that you pick off a piece of the wave coming to you, and you measure its phase very quickly, and you send this to a deformable mirror, which changes its shape back and forth to catch the waves up with each other and make them come into your instrument in a coherent fashion. That's what's called adaptive optics. It adapts to the changing atmospheric conditions by putting in a counter effect of a mirror which the light bounces off, which moves back and forth to compensate for the wiggling of the light beam coming in from the sky. So the adaptive optics system brings your light from the star into the diffraction spike, which is the limit, to a ratio of about, it will put about 50% of the light or more into that spike. And so that gets rid of all the scattered light around. So this here is a picture of a star called Gliese 504, just a catalogue number, nearby star. And this is the residual after the adaptive optics system has done its bit. The planet is that guy here. Okay. Now you can see that getting in closer, if there were planets in here, it would be damned hard to see them. Okay. Here, this whole thing is just blotted out with what's called a coronagraph, which blocks out the main light of the star. And there's the planet. Scattered across this are just speckles of light and noise across this. Now, you'll notice, those of you who are optics fans, that the separation of these two things is about a couple of arc seconds. That doesn't sound like a great achievement, knowing the resolutions that are available with astronomical instruments today. But you've needed to have gotten all of that light, sort of the million times. The light here would have been 1,000,000 times brighter than the planet by the various adaptive optics tricks. Plotted on here is the radius of Neptune's orbit. So you're probing the outer regions of these solar systems. You're not getting into Earth radii, Earth-type orbits at all with these objects. So it's about it's about sort of halfway to Pluto or something like that. This guy. Now, something else to say about this planet. The planet is self-luminous. This is not reflected light. You might object to, if we're looking at planets so far out, then they'll be faint because they're bouncing the light off. This is self-luminous because this planet is still radiating the heat of its formation. Jupiter, as you know, radiates about, somebody help me here, I can't remember these numbers, about 2 or 3 times as much heat from its interior as light from the sun. So to do the imaging, you want to go to an infrared wavelength, not an optical wavelength. So these images are taken, I believe, in H-band at about 1 micron, coming into the infrared, where the object is intrinsically brighter. The contrast with the star gets bigger as you go into in the infrared wavelengths. That helps a lot too. I had something else to say. Yes. It will also help if the planet is as young as possible, because if it's shining by its own heat, that heat was basically left from the initial formation of the object. Gravitational energy falling down to the planet heats it into the interior, and it's since been radiating it. So the older the planet, the fainter it is. Now, telling the age of a star is absolutely the very devil. In clusters of stars, we got an idea because we look at the Hertzsprung-Russell diagram, and that gives us an idea of the age of the whole cluster. An individual star out there is very difficult. And there's tons and tons of work going on now. I'm a star fan myself, I always have been, and it's really entertaining to see how the beautiful work that's being done on understanding stars, because people really want to understand the planets, and realized very quickly that the limits to how well one can know this is how well one knows stars. So big efforts are going on now to find ways to measure stars' ages. They're still pretty uncertain. This is I think the lowest mass planet that was found by the SEED survey. It only found about this many out of the several hundred that we looked at, because it's so difficult to see anything closer into the star. And it's interesting and gives quite a good limit. I'll show you the limits in a minute on how many planets of this size there are around stars. There's now the statistical strength to do that. Let me find another one. Yes, this is a star called GQ Lupi, Lupus the constellation. Lupus. This is the planet. Okay. Again, blocking out the terrible mess on the inside, 1 arcsecond. This star is somewhat further away, so even though it's closer into the star, it's still at trans-Neptunian type distances. It's bright because the star in question is what's called a T Tauri star, which is very active and is a young star, just a couple of less than 1 million years old. So we have quite a good idea of the age of that star. New one. Yeah, what's this one? This is an X-ray bright star in which there are 2 planets, B and C. And again, the center blotted out. And again, at a distance so that this is large scale, large solar system. This one was discovered by the Hubble Space Telescope, and since then has been, planets closer to the star have been found by these adaptive optics systems. This star was investigated because there was a residual disk of gas around it, and therefore gas and dust, therefore they knew it was young. And there are 3 planets here, and there's a 4th, which is way outside the field of view. I put this one up because it's an image taken with a new instrument called CARIS, which we just built. And I think you would agree the quality of this image is really beautiful. A big jump on the previous images. It's a new instrument designed to get spectra of planets, and I'm going to show some pictures of it in a minute, and to allow one to get in closer to the parent star. We didn't find anything new. Look at that. You look at things like you think, ooh, 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 but of course you have to come back and observe them again and see if they're still there, and they're not just speckles. The mess that the atmosphere makes includes these things called speckles, which are little points of diffraction limited light, because suddenly right through the atmosphere there's a clean space. And speckles are absolutely the devil, because they're little bright point sources. They look like planets. So you have to observe over and over again. This instrument CARIS, Coronagraphic High Angular Resolution Imaging Spectrograph, is being built, or was built at Princeton by a group in our Mechanical and Aerospace Engineering department, headed by Jeremy Kasdan, maybe a friend of some of you, or he's spoken here. In particular, it was built by Tyler Groff and Jeff Chilcott, quite a few people, and Tim Brandt, Marianne Limbach, really, really smart young people. Just a beautiful instrument. We'll come back to this picture a little later. Which is this guy? Yes, this is a star around a rather interesting, planet around a rather interesting star, which is Kappa Andromeda. Big bright star, you can see it with your eyes. Early type star, couple of solar masses. What kinds of stars have planets? Do they go around little stars, big stars preferentially? And here is the companion. And again, way trans-Neptunian. Oh, thank you. Sure. Am I choking? And in fact, this is very apposite, because the next picture, if I got this right, is this.
We're in state parks and
we can't do this, but we can do water. The discovery, these objects, which are several times the mass of Jupiter, many times the mass of Jupiter, have been nicknamed super Jupiters. And to celebrate that particular object, a microbrewery in Vancouver, near Howe Sound near Vancouver, brewed Super Jupiter beer. You'll notice that I take it back. One of the bottles, these are full bottles. I have a bottle on my shelf now, but it's not full anymore. And it was grapefruit flavored India Pale Ale. And the grapefruit thing is some idea that Jupiter's a big grapefruit. I mean, go figure. It's quite good. I think it was a one-shot brewery, but the delightful thing was what the brewer of Howe Sound says. She did this because the good things in life should be celebrated, and finding a planet is nice to know it counts. Okay, let me skip. Oh, no, I won't. This is the image with the beautiful new array in Chile, the ALMA array, showing the emission here from a rotating disk being detected in the emission lines of carbon monoxide. This star, you can still see the large disk of leftover stuff in which planets are forming. And the new array in, it's done with the Smithsonian array, my apologies, on Hawaii. But the new array in Chile it's just pouring these things out now. And giving beautiful pictures of disks in which planets are forming with lots and lots of structure that tells you where the planets are. You can't see them, but you can see their effect on the streaming of the gas. Okay, next one. This is a simulation of all of the planets that have been found so far to try to find out a couple of things. Wrong gizmo. What is the largest size of the solar system, of the planetary system? You put a model in. This is going out to about 100 AU, 100 times the Earth's orbit. That's the best fit. What is the dependence of planet mass on distance from the planet? And this set of calculations and simulations made using a lot of models, say a word about this in a minute, tells us that the giant planets that we've seen so far with these detectors, which, as I say, have only to this point been seen out at trans-Neptunian type distances, are the tail end of the star formation. So they're forming like stars. To do this requires all sorts of involvement with modeling, and these are some model spectra produced by our great colleague Adam Burrows and David Spiegel at Princeton, of the spectra that you would observe from planets of these various masses at various ages. And I'll just pop them up. This goes from about a micron to about 15 microns. This is the region in which we're working. These big bands here, big chunks taken out of the spectrum, are water vapor, which exist in the atmospheres of these guys too, as well as in our atmosphere. And show, you can see water vapor, blah, blah, blah. What else can you see here? There's methane, potassium, ammonia. You can see the spectral features. So getting not just an image of one of these planets, but a spectrum, however crude, begins to tell you what their atmospheric composition is. So that's the motivation, this is a refinement of CARIS, built by this group and a couple of other people. CARIS is a wonderful instrument, and these folks have done a great job. Let me just show us a couple of geek pictures. Here's how it works. The image comes from the telescope. It goes into what's called a lenslet array. Instead of straight onto a CCD, it goes onto an array of little lenses, each of which makes a spectrum. It disperses the light through a small prism and disperses the spectrum onto a detector. So each of the pixels that comes in, you've taken a tiny piece of the sky, centered on this great walloping star, cut it up into little pieces, you get a spectrum of each location on that. So you can now, you know what the spectrum of the star is, and you can pull that out and see what's left behind. This is the results. There's all the mess that it makes a thing called a data cube, going from blue light to red light. You get an image in each slice of the cube, and all this disgusting mess that's the leftover optical residues of the optical scattering. And there is our friend, our imaginary planet, and you can see take a cut through this thing and get the spectrum of the planet. That's the basic idea. And here, by gum, was the first spectra taken. Let me see, let me skip over this. It's sitting at the back of an extreme adaptive optics system. I couldn't dig up a good picture of this gizmo. You take the lid off it, and it's so full of optics which are busy reacting and scattering. You wonder how a photon that got in there ever can find its way out. But there is several feedback loops designed to bring as much of the light into the diffractions image as possible and remove as much of it from the surroundings, and therefore increase the contrast. Let me skip over this. So this is a couple of frames from the lab taken at 1 micron and 2.4 microns, the extrema of the range, through the array. What else? Here it is. It has, that's the box it's in. It's about yay big. This is a dewar, as you can see. There's the seal for the vacuum. When you pop the top on, that seals it, and then you pump it down, because you need the detectors to be cold, sort of liquid nitrogen-ish temperatures. This is the filter wheel that some of you, I'm sure, have put on your own telescopes, that you can rotate it and put in different prisms, and a clear filter, and a neutral density filter, so that you reduce the brightness of the star so that you can measure its flux, and so on and so on. That perches inside of the machine, and there is one of the prisms. Okay, Marianne found this. A glass which gave you a much flatter spread of resolution with wavelength across the whole range. Your typical glasses go like that. You get much poorer resolution at the shorter and the long wavelengths, or vice versa. This one is pretty flat. And we're not talking about simple prisms here. This is several elements carefully aligned to give you the dispersion. The word high resolution here is a bit of an exaggeration. It's not high resolution compared to anything that a respectable stellar spectroscopist would call high resolution. But it puts all the resolution elements of the prism into one of the 3 bands. There are 3 bands here. They're called J, H, and K in the infrared astronomy world. And there are gaps between them here deliberately, although we don't have gaps in the instrument, because that's where our atmosphere has huge water vapor bands. And so they're practically limited by these, and we'll see a picture or 2 in a minute. The high resolution prism will get a resolution of about 70 in each of these bands. The low resolution, I think, gets a resolution of 20 or so, and gets all of 3 of them simultaneously, which is great, because you get the spectral energy distribution, and if it's bright in that band, it's cooler than if it's bright in that band, and it's cooler yet if it's the brightest in that band. So this tells you the temperature of the object. As I say, you're looking at self-luminous objects. You're looking at their emission. How am I doing for time, by the way?
Fine.
Group? Okay, here's Caris's inside, which looks complicated enough. There's the filter wheel. What do we have here? Where is the... I'm lost. I'll just leave that to you to look at as a thing of beauty. Being wrapped up with its insulation before cooling down, the prism. And then this is the contrast, which is the money plot. This is angular separation from the position of the star. And this is the contrast that you're able to get between any object that's at that location and the central star. So with the previous machine, the Adaptive Optics 188, so-called because it had 188 actuators, you got contrasts at half an arc second of about few parts in 10 to the 5. With this you get factor of 10 better. And it obviously goes down as you pull further away from the star, as it would. And you can get in to the diffraction limit, which is about here, with not terribly reduced contrast. Really nice instrument. That's the flats, the image, and then the first set of spectra. Okay, it sits back of this gizmo called the Extreme Adaptive Optics. And the left-hand panel, sorry, I shouldn't do this. The left-hand panel shows an image taken, you block the center out because it's too bright, taken with just the original adaptive optics system, A0188. The right hand, so you turn the extreme adaptive optics system off. That's what you get. You turn it on. That's what you get. You can see right away looking at that if there's a planet over here, you're going to be able to find it with this and not with that. And this pulls us in now for the nearby stars. Previously we were here at trans-Neptunian distances. Now we're several times closer at distances that are comparable to a few astronomical units. In other words, the size of Jupiter's orbit. Okay. Here is Caris. It's that bright red because Tyler is an Iron Man fan, and so that's Iron Man red. Sitting. Say again.
That cost extra.
It had to be some color. I don't know if there's a copyright on that color. Good point. Sitting at the Subaru telescope, back of the Extreme Adaptive Optics system, which is here. So it was taken out, taken up to the mountain, reassembled, and has gotten first light on the mountain, which was that image I showed earlier, and just to illustrate the improvement. Okay, now what can a gizmo like this do for you? It can get a spectrum, and the spectrum does two things. First off, it says whether the little point of light that you're seeing just beside the star is real or not. You pick it up at each wavelength. It doesn't move with respect to the star. If you walk through in wavelength, because the angular resolution gets worse with longer wavelength, right? The speckles and all that other mess will walk out and get further from the star with wavelength. A planet will stay where it is. And so you can subtract the image taken at one wavelength from the image taken at another, and all the mess drops out, but your planet stays there. So that's one of the big pushes for the contrast. And the other thing is that you get a spectrum, and so here it is. Here's the first spectrum. Here, the grey. This here gets very noisy because that's where the atmosphere is. Okay. So the data are very noisy, but there's plotted on top of models and can tell you that this here is an object with the spectrum of an M star, a little faint M star, about M6 or M7. And at the age of the stellar system that we think it belongs to, at the age we think the stellar system it belongs to has. That corresponds to a mass of on the edge of the brown dwarf star limit. So a 70 Jupiter mass thingy. So backing off a little minute on that subject, which something I should have said earlier. Measuring the fluxes, the brightness of the planet gives you the temperature and all that. It doesn't give you the mass, because the brightness of it changes with time because it's cooling. And the age of the central star is quite uncertain. So this spectrum, the best age guesstimate we have for the star, it corresponds to something about at the brown dwarf star limit, about 80 Jupiter masses. Okay, what else? And this is just published, the first discovery with the, at least the first published paper from the Extreme Adaptive Optics System. It's stepping away from stars now, from planets, and it's showing the emission is from the emission from dust, a disk of dust around the star. And so you can see the structure of this dust lane around the central star and measure the mass, the extent, the presence of planets. It's kind of hard to see planets in this kind of mess, unfortunately, but you can see their effect. So there's a two-pronged attack on studying massive planets in around nearby stars. One is to look at the structure of their disks. The other is to look for the planets themselves, because the planets are born out of the disks, and we'll see the effects of the planets as in the structure of the disk. And I think that's it. So this instrument just went to the telescope a few months ago, and is scheduled, I think, to be, there's an observing run at the end of this month, and it will be on for several times now, going through a list of stars which we already know have planets, so you can characterize them, get their atmospheric chemistry, find the methane, the carbon dioxide, the carbon monoxide, the water, various other species, ammonia, and all this sounds kind of familiar when you're a Jupiter fan, am I right? To get the atmospheric temperature composition and so on. To find new planets closer in, that's of course the thing that has us all drooling, and to measure the structure of the disks around the stars from which the planets might be forming. Okay, so that was all I had, and I'd be more than happy with questions, and thank you.
Slide that was right after the T-Tauri.
Sure. This would, if you keep going back, I'll sing out. If we could go backwards.
Of course.
Okay, or can I can go backwards. What's
Isn't that far from the beginning?
right? Sorry. T-Tauri star.
It was the one after that, or maybe two after that. It was the first image that, no, before this. Keep going.
That's the T-Tauri star.
Oh, okay.
So,
So then you have to go the other direction, sorry.
okay, sorry. That was the T-Tauri star. This is the another T-Tauri star.
Is there
So
another one? Yeah, that right there, this one. Star on the top,
that thing,
the one at 4 o'clock.
for that one.
Right. They seem to have a dark area radial to the center that is before and after them.
Yes.
Would that be an indication that you could use to say that that's a planet, or is that just speckled?
No, it's an artifact of the data reduction to some extent. One of the ways in which you remove the speckles and all the mess. I mean, you wouldn't believe what a mess these
Before you get it.
the before picture is.
Yeah.
Is to let the field rotate, and then take pictures of it as it does so, and then de-rotate it, because you know how much, and subtract one from the other, and sometimes that will result in negatives when things are not perfectly aligned. The rotation and derotation are possible because Subaru is an altitude azimuth telescope. You just basically turn off the image rotator. It's a very handy thing about new big telescopes. You just stop them from compensating for the Earth's rotation. I mean, they track, but the field will rotate within the focal plane unless you have a derotator to keep it. So you just turn off the derotator and take the images. And so it's very nifty to do these observations as the object passes through its culmination, because then the field is rotating the fastest.
We were thinking that was just a nuisance, not having a field derotator. Actually, it's a source of information.
It's a source of information now. It's a handy way. I mean, you could put a derotator. You could do this with another gizmo, but you just take advantage of the fact that. Please.
I had a couple frames. You had a slide showing water vapor in the atmosphere of one of the, the one before this.
This one.
You were saying you were seeing spikes of water vapor.
Right. These are models, but I mean, you see it in the real data.
Now this is on a self-luminous planet?
Yes.
You're seeing water vapor?
Right. You see water vapor in the sun's atmosphere too. But some water vapor features, but they're not very strong. But these self-luminous planets have temperatures of 1,000 degrees or less, 1,000 degrees Kelvin.
So by seeing water vapor, though, you would make the assumption that maybe there was life there if there's oxygen in the atmosphere? Or where do you go with that?
Water's very abundant in the interstellar medium and very abundant in the atmospheres of planets.
Okay.
So, and you see it in the atmospheres of brown dwarfs and cool stars.
I didn't know that.
That's it. So oxygen is the thing everybody would be after, because it's so reactive that it has to be maintained by a sort of an engine like life.
But for the oxygen to have been there in the first place, how did that come about?
Well, we think the Earth's atmosphere was, the oxygen in the Earth's atmosphere is the result of anaerobic life.
Yes.
Right.
So do you make that assumption when you see this on a...
No, this is water vapor that we're seeing, which is present.
Okay.
And oxygen is very hard to get at because it's in the Earth's atmosphere, and so any spectral feature which is in a planet would be blocked by the similar features in the Earth's atmosphere. And there aren't any very handy oxygen transitions around here. You can see the water features, the water absorption features in these brown dwarfs and planets, even against the Earth's atmospheric water vapor, because the pressure in the Earth's atmosphere is much, much lower than it is in these stars, and so their lines are much more broadened.
Thank you.
The previous slide where you had the 3 planets,
Where was he?
that one. Just to clear, when we take astrophotography, we stack our images. Is that a stacked image of
Yes.
how many? You know about how many images they stack to do this?
I haven't the faintest idea, but
Okay.
I'm guessing a few dozen. Taken with exposure times of seconds.
Really? Wow.
But I mean, I hope none of my young colleagues is listening to this, because I don't know what I'm talking about. That's just a guess.
Have you detected orbits of those?
These ones, yes, not me personally, not us personally, unfortunately, but there is there are 2 systems. The other one is around Beta Pic, where planets have been seen with space telescope. The Hubble telescope can see the outer. I think you can see these 2 in the outer planet. I don't think Hubble can see that. In any case, over the years, their orbital motion has been seen, which is fabulous. There is a test we need to do, by the way. You see something like this, right? big walloping star in there, and these are little images. Well, the sky's full of stars, especially faint ones. And so to be sure that these actually have anything to do with the planet, with the star, you need to do this a few months later, because the proper motion of the nearby star will have changed the relative positions if these are only background objects. So you have to do a proper motion test to be sure.
Is it possible they would have also moved in their orbit?
Yes,
And
and-
so you have to correct for that.
They wouldn't. The proper motion's much bigger, but usually. But yes, now as you now put the pictures together after years, so you look this guy up. It's called HR 8799, and you'll see that there are orbiting, there are motions have been seen with Space Telescope, and the other one is Beta Pictoris. So.
Cool. Out as far as Neptune or something. So
Yeah, so they don't move
very
that much, right?
It looks like it's right. No, that's Mercury. But it's really
Nah, dream on. Not for a little while. But then I never thought I would live to see anything like this. So
It's very exciting.
Thank you again, Dr. Joe.
Thank you for
thank you, guys. Oh, I forgot to say something about this. I thank you for this. It will go to a good cause. I know this part of the world quite well, actually, even though I'm down in Princeton, because down the road, down 22, is the Mountain View Youth Correctional Facility. And just down here in Clinton is the Edna Mann. And we teach there, or have taught, and teach college courses, and we need to buy them books sometimes. So.
There you go.
Yes, thank you.
Oh, thank you again.
Thank you.
Yeah.